Here are solutions to homework set number 15 for ECE 341 for summer 2023. This homework looks at F-tests and analysis of variance. The first problem, if you go to Hector Airport in Fargo, it's got the temperature in Fargo since 1942. If you look over the last 10 years at the temperature in December, January, and February, the average temperature that is, it has a mean, standard deviation, and sample size. So here's kind of what the PDFs look like. Blue is December, red is January, pink is February. Do these have the same mean? Well, one of the reasons you might want to do this is I'm at a company, I've got 3 parts have come in. Are they the same? Can I just lump them together, throw them in a big bin? That's kind of what analysis of variance does. Are the means basically the same? So to do that, I calculate the global mean. I calculate the mean sum squared difference between columns, the mean sum squared within columns, and then take the ratio. The ratio is the F-score. So again, kind of what the differences are. MSSB, there's a global mean somewhere. Let's take all the means relative to the global mean squared. Then for each individual, I've got its own mean. Find its spread, its variance, sum squared within columns. The ratio is your F-score. A large F-score means that the means are different. So here's the calculations. I take the mean of A, standard deviation of A, likewise for B, C, sample size. K is the number of columns, number of data sets. N is the total number of data points. The global mean is just take all the data, add it up, divide by the total number of data points. That's the global mean. Mean sum squared between columns is how far the means from the global mean squared, weighted by sample size. Mean sum squares within columns is what's the variance of each data set. Then the F-score is the ratio. So doing that, I get an F-score of 0.82. Throw it in StatTrack. The numerator has 3 columns, meaning 2 degrees of freedom. The denominator has n minus k, 30 minus 3 degrees of freedom. F-score is 0.822. There's your probability. So what that means is there's a 54% chance that the means are different. Basically no conclusion. You might be able to lump them all together, which kind of makes sense. December, January, February are all winter months. They're all cold. You can also do that with a table. Some classes do that. I would just use MATLAB code. Same thing. Problem 2. Let's look at world weather. NASA Goddard has been recording global temperatures since 1880 and calculating the deviation from normal. And this is degrees C times 1,000. So this is actually minus 0.169 degrees C, minus 0.237, minus 0.302. Is there a difference in the means between these 3 decades? So here's what they look like. This one is 1880. This one is 1890. And here's 1900. And it actually was getting colder. Back at the turn of the century, there was fear that we might be entering another ice age. Well, we did put enough CO2 in the atmosphere, we blew that away. But anyway, that's what the weather was. Is there a difference in the means? Well, that's analysis of variance. Same procedure as before. I have my mean, standard deviation for A, B, and C, sample size, calculate the global mean, mean sum squared between columns, mean sum squared within columns, F-score. All done. F-score is 4.11. To see what that means, throw it into an F-table. I've got 2 degrees of freedom in the numerator, 27 in the denominator, so this is n minus k. This is k minus 1. 3 columns, 30 data points. F-score is 4.11. Corresponds to a probability of 97%. So I'm 97% certain that the means are different. What that means is that the climate is changing. At the turn of the century, back in 1900, it was actually getting cooler, with fears of coming ice age and so on. Okay, you don't have to have the same sample size. I could have sample size of 10, 20, and 30. That's not a problem. And let's take a bigger spread. So here's 1880, here's 1940, and here's 1992. With 30 years, 20 years, 10 years. Mean standard deviation, again, this is times 1,000. So there's actually 0.628 degrees C, 0.041 degrees C, minus 0.169 degrees C. Is there a difference in the means? Well, looking at it, I'd say, yeah, it's pretty obvious there is. Does that show up in an analysis of variance table? So again, same procedure as before. Type in the mean, standard deviation, sample sizes, grind it through. Global mean is 299. Mean sum squared between columns, 3.3 times 10 to the 6th. Mean sum squared within columns, 2.8 times 10 to the 4th. Ratio, 120. So there's my f-score. To see what the f-score means, convert to a probability. In this case, I've got, oops, I misspelled 1. K minus 1, degrees of freedom in the numerator, 2. I have n minus k, degrees of freedom in the denominator, that's 60 minus 3. F-score is 120. There's the probability. It's not actually 1. This is actually, I think StatTrack has got now 5 decimal places. It's at least 0.999995, something like that, rounded up. Basically guaranteed the means are different. Doesn't tell you which one's the outlier, doesn't tell you what the trend is. All the f-score tells you is yes, no. Are the means the same or different? In this case, they're definitely different. So that is analysis of variance. Again, where this would apply is if I have parts coming in from a company, from a vendor, and here's the data for them, I might reject them saying, you've got lousy quality control, the means are different. Homework set number 15 for ECE 341.